Great. Peter, do you want to take notes?
Yeah.
I can send you the notes doc.
Okay, do you have a note stock already read? Or
There is one somewhere.
Okay.
And then maybe we can start with like really quick introductions. Just like your name, where you're working, maybe like in like one sentence why you might be interested in JAX. Sorry, let me just find a notes doc.
Oh, I'll start new one second.
No.
There's
We have
actually-
a special
there's a
one.
quick
We don't need to take notes on everyone's intros actually, so I'll start. I'm Sky. I work on the JAX team at Google. Let's go this way.
My name is Alex. I'm from Amazon. I'm working on NailMX compiler.
My name is Jack. I'm working at Revos. Interested in JAX for being able to run it on our hardware.
I'm Eric. I'm ARM, interested in JAX on ARM devices.
I am Stella, AMD. I don't know what I'm doing yet.
I'm David Hall. I'm at Stanford. I work on a LLM training toolkit called Levanter that's in JAX.
I'm Jake. I work at GraphCool and I also try and make JAX target our hardware.
Nice to see you.
Nice to see you.
I've always seen my email.
Hi, I'm Sharding. I'm from VBA Accelerate Group. So I'm interested in this JAX because JAX is the main framework we are currently working with.
I'm Dwarak. I'm from Cohere. I work on Fax, Cohere's distributed training framework, which is based on JAX.
Albert from Keeley. I work on infrastructure inference. Everyone else side?
Yeah, I'm Bharat. I'm also from Cohere. I work with Dwarak too on JAX training.
Hi, I'm Peter. I work on JAX at Google.
Hi, I'm working on PyTorch Accelerator at Google. I'm interested in Pallas as a torch backend.
Hi, my name is Bonse. I work in PyTorch Accelerator and from Google too.
Hi, I'm Joe. I'm from Apple. We have been using JAX for large-scale distributed training for a long time. And we have been testing with Pallas and the Trident kernel for quite some time.
And there's some people on GBC on the video call, I think, right?
Yeah, so let's do Mehdi.
Hi, I'm Mehdi. I work on deep learning frameworks at NVIDIA.
And Tony.
Hi, everyone. I'm Tony. I work in Sumanova system.
And Sharad.
Hey, I'm Sharad. I work on the JAX team, mainly on Pallas.
And who just joined? Chow. We're doing very quick intro, just name, company, maybe one sentence why you're interested in JAX. If you're comfortable with that.
Hi, I'm Chow. I'm from AMD.
Cool. Okay, and just so the structure of this meeting, the first half hour is kind of free form, so hopefully you guys have like questions or discussion topics. And then either at the half hour mark or when we run out of other things to talk about, Sharad, who's actually the main Pallas author, is gonna dive into a Pallas deep dive, and he has some slides prepared, but hopefully it can be kind of like an interactive session.
So what would you like to talk about?
Who wants to kick it off?
My question on Pallas. So suppose I already have a kernel written in Trident, like using the program ID and doing some like a integer arithmetic to figure out like where's my tile and stuff like that. How easy is to translate that to Pallas, to the block spec thing, or can I keep the old program ID based integer stuff?
Sharad, do you want to take all the Pallas?
Should we just maybe see what the agenda items are before answering any of the questions?
Let's get into it.
I guess go into it.
Yeah, I think it depends on your kernel. Usually, like a lot of common indexing patterns that use program ID can be incorporated into block spec. But yeah, it's not like exactly, it's not representative of all possible patterns you could do. You could do sort of things with pointers that you could could have like overlapping blocks, but block spec is really about destroying blocks. Though, we're thinking of like variants on block spec that can capture more of these patterns, especially ones that translate to both TPU and GPU.
Also, Sharad, correct me if I'm wrong, but you don't like have to use the block specs. You can also kind of do like the direct load and stores. Is that true?
You can, but on TPU, it's not super advisable.
Right, because yeah,
for memory bandwidth reasons.
but on GPU, it would probably like more
On GPU, yeah. On GPU, block spec lowers to kind of what you'd already do with Triton, but on TPU it'll lower to something else.
Right. So my issue is that suppose I already have a backend which generates Triton, let's say torch inductor, right? I want to make it for Pallas, but because their generation is automatic, so if I have to think of how this integer arithmetic becomes a block spec, and that's something that I'm not sure if it's doable automatically.
That's hard.
Yeah, I think it might
Yeah.
be easier to start with like how like
Load
you
and
can
store.
use like that NumPy indexing to load and store, which I think is like more easily.
Yeah.
It's closer to the Triton thing. Yeah.
Yeah, you could definitely use that directly in Pallas as well.
Has there been any? Have you done any work in trying to like infer block specs from the program? Like if you've got a program like that, you could. I don't know. It sounds hard.
We've thought about it, but I guess we've been pushing on easier fronts, I should say.
Yeah.
So it certainly would be interesting though to tackle that. Another thing is like kind of one of the fundamental problems Triton is trying to solve is like auto pipelining your code, like finding a loop in your code and figuring out how to like do the software pipeline that we already do on TPU. We've thought about that as well, but we came to the conclusion that it's like not worth the huge investment right now. It might be something we do later.
Because we're on the topic of kernels, right? So on when we're writing CUDA kernels, there are a myriad of things that we can do to maximize performance, like the maximizing the cache line and vectorized data loads. I'm wondering for TPUs, do we have an equivalent of all these optimizations, or is it all handled for us? Like if I'm translating a CUDA kernel into a Pallas kernel, do I have to worry about like very low level things like vectorized loads and stuff, or is it all handled for us?
I think it's like, so I'm by no means a CUDA expert or an expert on like maximizing your GPU kernel performance. At least on TPU, at least I feel like a lot of things are simplified. When you write, at least like the level of memory access control we offer in Pallas and Mosaic is the equivalent of saying like load this big block of memory, and usually like it's better if it's like a nice contiguous block, but we do the TPU supports strided DMAs as well. So there is a degree of flexibility that I know the TPU itself offers that we expose directly. Peter, do you have any thoughts, at least differences between GPU and TPU as far as like these sorts of lower level memory optimizations are concerned?
I mean, I have thoughts. I have insight.
Okay.
So, I mean, one thing is that the abstraction of both Triton and Pallas is designed to be cache friendly because it's all about writing a kernel that works on a small like L1 cache size tile of memory and managing the scheduling, the software pipelining, or the warp parallelism across larger blocks of memory for you. So it's naturally very cache friendly. The program model is friendly to caches on CPUs and GPUs. But actually sort of almost mandatorily has to be like that on TPU, which requires static schedule of memory. For the vectorization, that is in scope. Like, so what we're doing is generating one of two MLIR dialects, either Triton IR or Mosaic IR, and you're relying on Triton or the TPU compiler to come up with a good, for that tile kernel, a good lowering that uses the vector hardware that exists on any given machine. That's completely different for different hardware. And that's probably how it should be. I don't know how good a job Triton does, but I assume it's a well-studied problem, and I'm pretty confident for TPU, it will load to the vector hardware reasonably well. So, but at the level of the tile kernel, every hardware is different, and they're going to have quite different performance characteristics. The intuition of the program model, I think, makes perfect sense in both settings, but exactly what your compiler is for that tile, big favorite.
Thank you. Just one more question. So when I'm writing a Pallas kernel, how do I write it? Like, do I write it keeping per device characteristics in mind? Like, how does a Pallas kernel play with PGIT or GSPMD?
Yeah, that's a good question. I guess the answer for that is shard map. Shard map is our current preferred solution. So the answer is that like PJIT doesn't know how to automatically partition kernels, and there's kind of at this moment there's no way for it to do that, just because it's basically a user written custom op, and at some point the user needs to provide some additional information about how they want this op to be partitioned. Because I don't think it's like unless we provide some annotations that are like, oh, these are batch dimensions or something, the compiler can't automatically figure it out. So with shard map, at least it provides like the biggest hammer we could offer, which is like give the user complete control over the sharding as well. Though we are investigating some things that are more in the middle. We have worked on a custom partitioning API, which is kind of like a hook into GSPMD. You could imagine if you write a kernel, you could write a GSPMD hook that says, "Oh, I am partitioning on the batch dimension," and then you re-emit a new kernel that is equipped to handle smaller batch size or something. Or maybe you could do something even more advanced like sharding over heads in attention. But that's not 100% ready yet.
Just to clarify how you would do it, it's like if you have a JIT computation, you drop into shard map, which says like, I am going to specify right now how the data gets carved up, and then you can call your kernel, because now you're sort of like in the per device view, but you have to tell it what to do with the data. Each device.
Sure. Do you have any plans to add automatic partitioning of Pallas kernels?
I mean, I think about it quite a bit. Like it certainly
Sounds hard.
something. Yeah, I think mainly the problem is that the GSPMD and all our partitioners run after JAX, so it somehow requires us to like preserve information past JAX lowering time, and then have the right hooks in whatever partitioner you're using to call back, and that seems to be the best strategy for now. It's not like something, the interplay between these two is tricky to manage, just because one's happening in XLA, one's happening in JAX. It's certainly like one of the big priority features that we're thinking about, though.
Question on the support for Pallas in the future. So because Pallas lowers to LLO, and LLO is different for every TPU version, so that does not mean that every new TPU that come out, somebody has to write the lowering, and the quality of that lowering might vary and introduce a version and stuff. So what are the plans to make sure that in the future it's still well supported?
I can't speak. I don't know enough details about future TPUs to know like what complications might arise, but I can say at least we've used Pallas on, I think, 3 generations of TPUs thus far, and actually 4 generations, everything since the V2. And it is there's not a lot of work actually necessary to preserve like backwards and forwards compatibility. There are some differences, but at least what we found is, empirically speaking, LLO is not like caused a big problem as far as like having to define new lowerings over and again. It's largely remained the same.
Anything else people want to discuss? It doesn't have to be about Pallas.
I kind of have a little bit dumb question about Pallas. So like in the inner mass that operates on the block, usually is written using JAX operations. So suppose that I'm just really bad using JAX operation, and I write a double for loop, doing like one element at a time. Like, is Pallas smart enough so that just like code I will make it in parallel, or that will be very bad?
It'll be very bad. Yeah. I guess part of the, I mean, it might work, but I think part of what we want to teach with Pallas to some degree is that like maybe you do want to think a little bit more about the hardware. In TPU, you know that all values you'll be working with are somehow laid out in 8x128 vector registers. So if you can be a lot more confident in your performance if you know that like the values you're operating on in JAX are at least 8x128 sized, and that's not, I think, too big of a burden on the user. especially if they're writing a custom kernel in the first place to maximize some aspect of the performance of their code. But in general, we try to handle, we will handle a lot of the inefficient code that you might write, but it may end up padding the registers out with junk values and doing a lot of wasted work. But so yeah, it's for your own good to kind of work with these 8x128s if you want to maximize your performance.
Or use JIT.
There was a question on the VC, which was a posted in a comment, but I couldn't quite read it.
Oh, let's see if we can look at that. Okay, so
From Eric.
Yeah.
The answer, I mean, I think that is so the question is basically, we have an open source flash attention implementation. We put a good amount of time into it and making sure it's performant, but it doesn't support all the various types of attention that people may want to use in practice. I think there's two ways this could go. I'd say that it's not our #1 priority, or at least not my #1 priority, to have a full set of fleshed out kernels as part of JAX. I would say analogous to the way that JAX doesn't really have a neural network layers component. I personally have been Adam and I have been mainly focused on making sure there's more abstractions available through Pallas, exposing more to the user. That being said, I think the main things that we will focus on are writing writing documentation and examples of how to write your own kernels. The flash attention one that's open source is not really that didactic, I would say. There's a lot of bells and whistles, but I think with sufficient knowledge, it's a good starting point to actually implement the various attention variants, like GMQA and local attention. So I would say we don't expect to open source any a fully featured flash attention implementation soon, but I also think that it's in a good place where people can modify it and try out these variants without too much trouble.
If I might add to that, I think there's also, we have libraries built on top of JAX that do have a bit more of that role of shipping a full neural network experience, Flax as an example. If there were particular attention variants that would be widely useful, I think, that's a conversation. Well, I don't speak for the people who own Flax, but I think it's highly likely that we could consider adding some such standard implementations to a library such as Flax. So if you have requests, then please file them, and we'll think about how to best to do it. But obviously, Pallas is a mechanism to let you write your own more than a specific one, right?
So, question on this Flash kernel. I've seen the source code, and it is written in functional programming style with the for loop construct, whereas I am used to writing nested for loops in Triton. So is that something that you are looking to evolve in terms of the Pallas syntax for writing nested for loops in the way people are used to usually writing them?
So for those particular, this is kind of, I would say, almost a JAX issue of sorts, as opposed to a Pallas issue. But I think there's some differences. So in regular old JAX, you are free to use for loops, but we often don't, because it leads to increased tracing and compile time. So at least we encourage users to use our for-I loop or scan constructs whenever possible, and use the unroll parameter to claw back any performance that they may have lost by using a rolled for loop as opposed to an unrolled for loop. On Pallas, the story is similar, but not quite the same. When you do this, the main thing is that in Pallas, we actually unroll all for loops as part of the lowering pass. So the for loops you see in the flash attention kernel are just mainly there to be syntactically consistent with the rest of JAX, but underneath the hood, we're actually unrolling them as well. So those in the flash attention kernel, you could easily just replace those with regular Python for loops, and it would be fine. However, I think we are working on rolled for loops in Pallas and Mosaic, and in Triton, you need to use the for-I loop to lower to the Triton structured for loop. So Triton Triton does some AST, I guess, like Triton basically parses the AST to figure out what your for loop is. JAX does not do that. It traces, so you have to use the rolled for loop construct in JAX. So I guess the story is a bit complicated depending on GPU and TPU, but I think in general it's safest to use the functional for loop.
So I'm hearing that I can write regular for loops in Python today instead of the for hyphen loop construct, and it's going to be equally performant.
On TPU, yes. On GPU, no.
Okay, and that's because of the way you lowered to Triton?
Yeah. It's a difference in how we lower to Triton versus lower to Mosaic.
Okay.
Yeah, I mean, basically on Triton determines whether you get a rolled or an unrolled loop, which might have performance implications or might not, but it is different.
The reason I'm asking because you all know that Pallas is graduating from internal Google users to the whole world, right? And usability is super important. And the rest of the world is used to writing nested for loops in a certain way. So it's about customer obsession. So
Yeah, I mean, this is like Sharad says, like true for all of JAX. This is sort of like the price we pay for using tracing, which lets people write Python code, which is like a language that people are very familiar with, but is hard. Like you can't parse Python code very easily. And so like, yeah, there is a trade-off, a usability trade-off here.
But even with Python for loops, there was a plan via PEP 523 to pass down control flow to XLA. Can't that be brought in here?
Is anyone familiar? I'm actually not familiar with that. A PEP?
I'm not familiar.
I recently saw at the LLVM Dev Conference, Max Leventhal really figured out how to abuse Python and trace through for loops and if statements and get the structure back.
Wow. Yeah, I mean, I think
It was terrifying.
right. The JAX philosophy has sort of been like, we don't try to solve super hard problems. Like we would rather sort of like do something simple that maybe has like a hopefully small upfront usability cost, but that doesn't like involve then like a huge magical component. And that's kind of the trade-off here.
Debatable, but people write for loops all the time. And I think it would be good to push that down to XLA.
I think
I think
what
so.
happened is like, I think it's no worse than JAX already is. That's kind of it's
Maybe.
already there. But I think if you go to PyTorch with Pallas, maybe PyTorch users will be a bit like, what's going on? I don't know what's happening.
I will say that like if we look at the parallel, which is like PyTorch and Triton users, PyTorch does let you write like Python for loops in their kernels, but again, because of the way they like extract that structure from it, it does limit the Triton language in some other ways. Because they're using ASTs, they like things like higher order functions become a lot more tricky, or they just don't work at all. And it's a lot harder for them to actually stage out a lot of like weird edge cases, is at least that's my experience with Triton. So they've picked at least another side of this trade-off where they allow a lot more Pythonic constructs, but it does limit a lot of the crazy stuff that we're accustomed to doing in JAX, like injecting functions into kernels and things like that.
Yeah, I think you could have different levels of abstraction with limitation. That's fine. I think regular grid kernels is such a bread and butter use case for deep learning. You know, getting that expressible in the way people write nested for loops, I think would be very usable.
Yeah.
And I totally agree with you that it may sacrifice flexibility, but that's fine. I mean, deep learning does not handle sparsity very well, right? So we kind of already in a constrained world and are living with certain things. And I think netting out usability is important. Portability of existing Triton kernels is also important.
Go on.
I can certainly also imagine that like the design trade-offs are a bit different for a kernel that's doing mutable writes in the middle of a loop nest, as opposed to JAX code that's very functional, and therefore a for loop is not something you want to write quite as frequently. we could maybe consider whether, I mean, historically, we've never wanted to look at Python source code. We just consider that off limits. But you could imagine that maybe people would want to opt in for certain pieces of code. I think we could like maybe explore the design space a bit more here. We actually had a prototype years ago that tried to fake nested for loops with the Python syntax transparently. Didn't work very well. Maybe it's time for another look.
Yeah, the reason I'm interested in being on behalf of AWS and Trainium, and Sharad knows I was in a meeting with him. So we are looking at Pallas as well. So I think we want to engage offline and continue the discussion because we have signals that the nested for loop construct is super usable for our customers.
Yeah,
that's great feedback.
Apparently the trick is to add an eval frame hook and then trim out the bytecode that does the jumps between loop iterations or conditionals, and then you can trace all sides of it.
Why didn't we think of that?
I mean, if we're able to crack this problem, it's cracked for JAX as well. So
Yeah.
Historically, we've run away screaming when people say things like that. So, you know,
That's actually something we have, like I remember with TF2's autograph, which was doing this, it's like this fundamentally no reason you couldn't hook kind of like that front end and then generate like the JAX per IR basically, and then give people like two separate interfaces.
I'm not advocating for this. I am just I'm just saying a friend told me.
I wanna, before we jump into the Pallas deep dive, which we should do soon, I just wanna see if like anyone else has, we've been talking a lot about Pallas. So I wanna take a minute in case people have other topics.
Question not about Pallas, but sort of related. So the ref thing, can I use the ref without like outside of the context of Pallas? Can I use like a regular JAX?
I think in theory, yes, but in practice, no, we don't expose that yet.
Does Sharad want to speak to that maybe?
well,
Actually,
I would say yes, but it's a secret sauce menu sort of thing. Or like, you know, like it's like it's only available inside JAX internals. So if you find it, then I guess you're free to use it, but we don't promise anything about it. But refs were originally developed outside of Pallas, so like they are somewhat supported with the rest of JAX transformations.
Should we move to the Pallas presentation book?
Can I ask a question?
Yeah.
I was trying to like design our team at NVIDIA. I was trying to design some SDPA API to use to expose the SDPA to X-ray. So our long-term goal is to use SDPA API to generate stable actual operations and lower the stable actual operation into something like quotidian fresh attention. So I was just asking, like, what is JAX right now with the stable actual? Like, do you support any kind of custom op through stable actual, or any plan for the stable actual compose op?
Yeah. So obviously we support custom ops right now. They're a bit wordy to write. You have to write, you know, a C++ kernel and some PyBind code and write a lowering rule that emits a custom call that has your custom call's name on it. So yeah, you can absolutely do it right now. We would like to make it much lighter weight, in the sense of you should need to write little or no C++ code other than your kernel itself to the call thing. I imagine for your use case, which is you actually like to emit something that the compiler recognizes rather than something that lowers to a particular kernel, that should be even lighter weight still. So yeah, we've received that feedback from NVIDIA, but it's actually the other sort of main sort of domain where people have been requesting larger macro ops is people lowering to mobile, where you have kernels that are baked and maybe you don't have a compiler. So we're looking into ways where we might allow sort of users to propagate basically a little sort of tag on the HLO to say, hey, this was a softmax. And if you know how to handle the special like softmax tag I put in, for free, otherwise here's the HLO, lower it as you would before. So I think we're trying to explore whether we might have a lightweight way to say that. I mean, I don't think we want to, basically it's something that a library author, like someone offering a transformer layer, should be able to put in their thing, should make it all the way through JAX, all the way to the compiler or ultimately to a kernel. But really JAX doesn't have a lot to say about it, but we should allow it to integrate seamlessly with everything else JAX does, and we should allow it to propagate all the way through. I think that would probably resolve your question if we had an API like that, right?
Yeah, so how extendable is this kind of API? Like, for example, like people want to have different kind of custom op. Right now it's attention. Maybe in the future they want different.
That's why it's a little bit difficult, because I mean, if we agreed on what these custom ops are, there's a simple answer: they should go in stable HLO. Okay. If we don't agree, then is there a mechanism or a protocol for how you add these things? And the only thing I can think of is I'm not involved. You're free to add them whenever you want, and as long as you have a compiler or a kernel implementation of the custom quality you've added, great. But I think really, if we can agree on what the common patterns are, they should go in stable HLO, or another MLIR dialect that we agree on is the way to express these ops. So.
Yeah, thanks.
I guess that maybe a little follow-up thing from that, because maybe I've been doing a similar horrible thing, is how comfortable do you feel with allowing the MLIR builder to be extendable to other dialects? So I've been like having custom calls where I go, here's the string of my MLIR IR, take that down, and my compiler eventually goes, I'll pass that and put it back in, and then carry on from there.
Well, if you go and look at how Pallas Mosaic is implemented, that's exactly what it does, right?
I'll copy that.
It's not really a feature we've exposed outside JAX, but yes, in general, we have things where we basically embed an island of some other MLIR dialect in stable HLO, for example, for a Pallas kernel. If there's some sort of more generic thing we could do there, obviously I'd be interested to know what it is.
I guess because maybe I haven't had the request in so many terms, but my users are kind of asking for when I'm writing my lowering for a particular primitive, I just want to be able to use my dialect in there kind of arbitrarily, and I have to say to them, "Oh, no, you can't. You have to sort of make your own module and turn it into a string and push it through here."
Yeah, that might be better. I mean, like already everything we're talking about is not sort of like a official JAX API. So the risk is that like we change it and then next time users upgrade JAX, like your code stops working because we're not like coordinating on this API.
At the point you've written the lowering rule, you're already dealing with our internal internals. Right. So really the question is, can you stick another MLIR dialect in the middle of the stuff you're otherwise passing through JAX? Absolutely, feel free. You'll have certain problems. For example, JAX vendors its own copy of the upstream MLIR Python bindings. So if you're trying to build some dialect we don't know about, you're going to have to serialize it or do something a little weird to make it work. But you're also going to hand it to a compiler that's not expecting it. So you're going to have to either rewrite it away or hide it in something like a custom call.
Or I go find the stable HLO people and ask them the same question.
Exactly.
Yeah, if you get stable HLO.
But in general, nothing stops you from mixing MLIR dialects and what the IRJAX is building. It's just that the compiler you're handing it to won't expect that. Okay. So if you intend to intercept and change that code somehow.
Well, it seems like maybe seems like there's at least like 2 use cases for like having a more maybe they're a little different, but yeah, like something a little bit that we can put our guarantee behind. But yeah, you're free to do whatever you want.
Yeah, I think I package it in a string, but people gave sort of request of.
I actually have to run for the PGRT one.
Maybe you get it as well. Just your users go, I just want to poke a little thing just here, please, and you're like,
yeah, we do that all the time on the PyTorch side.
Sure, everyone's doing it. It's kind of a.
If there's something we could do to better support the use case, I'd love to know what it is. But it sounds very
serializing it to string. It all functionally works. I was just kind of like asking for a lower friction way of doing it.
Okay. I want to get to the Pallas demo, so maybe
go ahead.
Should we talk offline? Okay, sure, take it away.
Yeah, I mean, it's more of an interactive walkthrough, I would say. So feel free to interrupt with questions. And it's not like, I would say it's not intended to be complete, and that I'm not going to go over like every single thing in Pallas, just what I think are like the highlights and what I find interesting and or fun. And I'll show, if we get to the end, I can show off some of the new APIs we've been working on. Yeah, so it's a collab. I have 4 TPUs on it, but most of the time I'll only be using one of them. And yep, I import Pallas as usual, and this will be a TPU focused demo, I guess, mainly because I want to show off, like, at least on TPU, we've been able to think a little bit more full stack about this integration, because we're working with XLA on Mosaic and have a better model of how TPUs work and how to get a good performance from them. But we're hoping that the analogies and the APIs here, at least the more experimental ones we're working on, translate nicely to other hardware platforms as well. Yeah, so I mean, this is like the main kind of mental model I personally use when programming on TPU. You have these like arrays that live in HBM, and then you have these other memory spaces available to you. And really, maximizing performance is about using your compute while using your memory. In this case, the main memory space we work with is VMem, or vector memory. VMem is basically like the L1 cache for TPUs. Once we transfer things into VMem, we'll then load them into vector registers, which are these 8x128 registers I was talking about before. And once they're in the 8x128 registers, we are now free to use the matrix multiply unit and other vector ops to compute what we want to do. Also on the side are there's scalar memory and the scalar registers, which are kind of like just a regular old CPU. And those are actually really useful, but I won't go into, I can speak to some applications, but I don't have any like demos of using SMEM in this collab. So the first basic kernel is one that adds two vectors together. You can see here that we have two refs for the inputs and then one for the output. And all we do is Pallas call it, provide an out shape for the output, and then pass in our two arrays. And I pass in debuggables true so we can at least get a glimpse of what's happening underneath the hood. The program that JAX sees is this kernel, and it basically has these ref types, and in it we stage out these read effects and write effect, and in between there's that add. So in general, like once you've loaded things out of these refs, you have JAX arrays, and you can do whatever you normally do with JAX arrays. And we take this JAX array and we lower it to Mosaic, and this is what the Mosaic MLIR module looks like. Pretty simple. It's like almost a one-to-one translation of the JAX array. So going back to this picture and what's actually happening, conceptually speaking, like when we're writing Pallas on TPU, the default case is that these refs are VMem refs conceptually. So these, you can think of these as just like roughly pointers backed by VMem. And when we do this get item notation on them, we are loading things in VMem into VRegs. So this value right here is somehow stored in vector registers. This value here is somehow stored in vector registers. We add them together using the vector add op. And that result of that is stored in the vector register, and then we vector store that back into this output VMem slot. And then the job of the code that goes around the kernel, it's to copy things from HBM into VMem and back. So right before we kick off the kernel, we'll copy X and Y into VMem. We'll execute the kernel, which does stuff with the compute unit and VRegs, and write back to VMem. And then after the kernel is done, we'll copy an output buffer. We'll copy to an output buffer for the output in HBM. And yeah, so that's basically the simple mental model for programming Pallas. At least this is like the first step you take. You note that there's basically two layers of kind of transferring happening from HBM to VMem, then VMem to VRegs, do the compute, and then all the way back. Yeah, I guess going back to what Peter was talking about with HLO, when you actually look at what's happening, and we've just emitted this like big old string that goes in there, which is just the serialized version of that MLIR module. Yeah, so here's a little bit more advanced of a kernel. This is a matrix multiplication kernel, and this one is using the block specs that we talked about in the talk, I guess, in Sky's talk. And the idea here is that instead of doing something like we did in this add vectors kernel, where we first copy X and Y into VMem, wait for that copy to be done, then execute our kernel, then copy back to HBM and wait for that to be done, we're going to basically stream chunks of X and Y into VMem while we're computing with VRegs. So we're going to be like, while we're waiting for the next X and Y chunk to appear, we're doing the computation for the current X and Y chunk. And that's basically the pipelining that block specs enable. So block specs are just a combination of basically three pieces of information. One is the kind of shapes by which you want to carve up your inputs and outputs, and those are these block shape arguments here. And these are basically like parameters to the function. The next is a grid, which says how many times am I going to run this kernel and what's like an indexing scheme by which I can figure out which instance of this kernel I am. And so we're using a 3D grid here. And then finally, an index map function, which maps the particular index of the grid to a particular block. So it basically says when I'm operating on this index in the grid, what are the blocks I would like to have in memory when I actually do that computation. And with this information, Mosaic can pipeline your code automatically. And in Triton, this exact kernel would do something like mapping over many SMs. And yeah, so this is actually very close to like a kind of like state-of-the-art mapmul on TPU. TPUs do BF16 mapmuls by default, so there's some, if you wanted to get even more out of them, you'd probably do them in BF16. But for F32, this is basically about like, this is very close to like all you need for a like close to peak performance mapmul, which I think is pretty cool. A lot of the work will then be tuning the block sizes, picking the right amount of memory to be copying at once while doing the compute on the bits that are already in VMem. Any questions about this?
Yeah, I have a question. Like, how performant? Like, if you're going to take this, and you're speaking only to Pallas and Mosaic right now, but if you're going to speak to like Pallas with like Triton and a GPU, like how performance portable like would this be? Would you have to be tuning the these block sizes for your GPU, or like?
So, you know, the portability story is complicated, though I think it's something we'd like to make like a lot more progress on. For this particular kernel, the complexity comes in the way we've structured the grid. We have a 3D grid, whereas normally, or in many cases on GPU, you'd use a 2D grid. And if you were to just use this kernel as is, you'd basically be doing atomics for the reduction dimension, which, you know, is a valid strategy, but it's something that a lot of people don't want to do for deterministic purposes. So in a sense, like this kernel is portable, but it may not be exactly what you wanted to do on GPU to begin with, even though kind of like what it entails is a valid thing to do on GPU. And the reverse is also true. If I were to say, make this a 2D grid and then run this on TPU, I would have to basically unroll the accumulation inside the kernel. But that would require copying a lot more things into VMem than you would normally, or more than maybe you would want for performance characteristics. So you could imagine that like the version of this kernel that works really well on GPU would be the one where bk equals k. So there's basically like a 2D grid. But on TPU, you may want to use a smaller than k-sized bk to you know, better overlap in the pipeline. So the answer is kind of like it depends, I guess.
I think there is one more difference here, right, in the semantics. In GPU, my mental model would be that the grid of kernels are launched concurrently. So the accumulation in the OREF would be a synchronization point. Whereas here, I think the understanding is the kernels are launched inherently sequentially so that I don't have to worry about contention to update the OREF accumulation. Is that correct?
Yeah, that's correct.
Okay, so this is part of the abstraction. Then I can assume that the kernels are launched sequentially. So if there is some reduction across them on common variables, they will happen sequentially.
Yeah.
Whereas on GPU, they could happen concurrently.
Yep. Though block specs don't have an opinion about sequential versus concurrent execution.
Yes, but it's leaking out right there, right? I mean, if the OREF updates are concurrent, we have a problem. They have
right. So these would have to lower to atomic updates on GPU.
Right.
Like
Whereas you don't have to do that for TPU.
Yeah.
Okay.
I wanted to highlight one feature of this, which was I'll skip the Mosaic, which is like the fact that you can VMap this. So, you know, you can create a batch mapmul and then now start doing the same mapmul on, you know, bigger matrices. And that's just done by adding a new grid dimension to the Mosaic kernel. And then this is kind of one of the more meta-programming aspects I talked about, where you can inject a higher order function here. This activation could be like a relu or something. And we can parameterize our matpl now with an activation function, pass that into the kernel, and then basically we call the old matpl kernel and then perform the activation at the very end if it's passed in. So it's a nice way of kind of composing kernels together and potentially templating just using the regular Python you're accustomed to. I have an example here for softmax. It's not super insightful, but I guess softmax is always a tricky kernel to get right, just because it involves several reductions when done stably. Here we're kind of just doing the naive thing where we load the entirety of the feature dimension into vmem and then do all the reductions in vmem as well. But when you can't fit the entire feature dimension into vmem, or say you want to fuse it in with with other matrix multiplies, we basically have to end up using something like flash attention, which is, I guess, what I'll go over here. This is like a really minimal flash attention implementation. It has like a minimal set of bells and whistles that you want. For example, it only handles float 32 right now. But basically, it resembles the matpl kernel at a very high level. We have like some accumulators, some inputs, and we have an output, and we do some compute after loading everything from vmem to vregs, and then we write it all back at the end. And then we schedule it using a 2D grid, where in this case we have, this is a kernel that only has a sequence length and head dim dimension. So kind of like, you can imagine just a single sequence you're doing attention for. So that's why we can keep the kernel pretty simple. And here we'll actually, well, I guess any questions about this before I move on to like the additional things?
I'm not sure if this was discussed before, but how do Pallas kernels interact with gradient calculation, autograd, and other function transfer?
Oh yeah. The answer is mixed, I would say. We do support forward mode, but I know forward mode's not really used that much in like deep learning applications. Reverse mode, you'll have to write a custom VJP. So that's generally what we do.
Okay, thank you.
Just to check my understanding a second. So the blocks described by the block spec, are they guaranteed to not overlap in any way?
Yeah.
So like they're unique for your little kernel instance, whatever it is.
Yeah.
Okay,
that's
cool.
like the contract of block spec. So yeah, so this is, as I said, attention written for a single sequence. So usually we have multi-headed attention and we batch that. So you can I'm getting towards where you can vmap it twice basically, but just as like a very simple performance benchmark. This is not by no means meant to be like thorough, but even the simple kernel can like outperform XLA on a 32K long sequence, which I think is neat. But it's also F32, so not really representative. So yeah, to get multi-headed attention, you can just vmap this function. To get to get batch dimensions, you vmap it again, and now you have the classic 4D tensors we work with. For multi-query attention, you vmap it, but don't vmap over K and V, so you're only vmapping over Q. And then for the batched variant, you just vmap that function again. And now this is the classic batched MQA signature we see. Yeah, and then the last thing, or the last kind of non-experimental thing, is combining it with shard map. So I said before we have 4 TPUs. So how could we compose all these things together to kind of split up our attention over the 4 TPUs? And you can do that by a shard map. We can call our we can basically specify that the leading dimensions of all our inputs and outputs we want to shard across our x-axis of our mesh. And if we now you can see that like inside this we should have like a two-sized batch shape somewhere. Yeah. So yeah, the batch dimension has been sharded 4 ways across these 4 devices. And each chip locally will be doing the same Pallas call. So yeah, this is kind of like the, I know someone asked about this, but yeah, this is basically the solution to how it interacts with JIT. Cool. I'll go over some more experimental things that we've been working on. And these are a lot more TPU specific. This is not, these APIs are not, we don't aim to make them portable at this point in time. The goal is just to expose more of the TPU and expose more interesting kernels, basically, to the user. So the first is DMAs. So this is basically exactly implementing that add vectors kernel or something very similar to it. It's just a copy. But the idea here is that if we pass in the block spec and then annotate that, we don't really care about what memory space we want it to be in, aka any. We basically have to conservatively assume it's an HBM and schedule transfers for it into VMem. So this is basically like the end-to-end story of what a kernel is doing, or at least what a simple kernel will be doing. The first thing the kernel will do is it'll basically allocate some scratch space. So it'll allocate like 2 8x128 refs in VMem. We'll also allocate this semaphore, which will be used to basically basically do things potentially in concurrently while we're waiting for memory transfers. So this async copy is the new function that lets you schedule a transfer from one ref to another, and then you can block on it, or you can do something else while it's happening. Once it's done, we can now do this vmem to vreg to vmem copy, and then we schedule a transfer back from vmem into HBM using the same async copy function. So you can imagine like these are kind of the building blocks by which the full pipeline is implemented underneath the hood for block specs. But we did want to expose this as another lower level programming construct because we're finding that we can emit a lot of different interesting sorts of kernels when this is plumbed up to Pallas. Any questions about this? This is like a lower level API than I think we've shown in demos before. And
yeah. So is this quite this code here is very TPU specific, but suppose I'm here with my IPU and I've got some cool IPU feature. Is there a mechanism for me to do something similar in Pallas?
Well, I mean,
like custom call, I guess.
I mean, certainly like they are TPU specific for now, but it's not like we designed these APIs with it's not like async scheduling of copies or DMAs is like a TPU specific concept.
What I mean though is this is, it could be generic. That's kind of fine. I mean, you've kind of gone, I've got a cool feature in my TPU. Here's a custom interface for interacting with that. Is there a mechanism for adding things for other platforms?
Oh, I see. Yeah. So yeah, I mean, it'll be akin to adding custom ops and JAX basically. So the story there isn't quite complete, but presumably if you had, I don't know, if Amazon wanted to have a Trainium version, they could say PL Trainium or something like that, and have a set of JAX primitives that have associated lowering rules. In principle, that something like that is possible, but it's something that we haven't come up with a official API to do so yet.
Probably be great to have more examples of such a thing if you have things you want to have things in mind. Maybe offline, but
yeah.
Question. So is this async copy something that can be used to implement the page attention, like used via VLLM? They're basically putting a page table in the code memory, like OS page table, to use that for keeping cache or something like that.
I don't think so, or at least not based on my understanding of page detention. My understanding of page detention is that the KV cache is kind of split over potentially many disjoint locations in HBM. And you kind of have another data structure that tells you how big the blocks are and how to traverse the blocks of the KV cache. We've thought about similar things on TPU, but at least for now, the KV caches in our attention kernels are already these big contiguous sections of memory. As in there are some intermediate in an XLA program. And if you pass it into a Pallas kernel, they'll already be contiguous seconds of memory unless you've kind of chunked them up already before that. So if you did want to implement something like page tension, you'd probably get several inputs, which are all the different blocks of the KB cache as inputs to the kernel, and then you could have another data structure. I guess what I'm saying is like this sort of stuff could be managed more outside of JAX, and then the kernel could know how to handle like several disjoint KB cache blocks. Does that make sense?
Yeah, thanks.
Actually, like one of the features, again, I didn't talk about in detail is SMEM. And, this feature, these async copies work with SMEM as well. And you could imagine having DMAs to SMEM, and the values that you get in SMEM could be used to schedule the other DMAs that you want to do. So it actually offers a degree of runtime dynamism that we usually don't expose on TPUs, which I think is like maybe the killer feature of a lot of these APIs, is like runtime dynamism and sparsity. And the final experimental thing I have to show you is a collective for mute. And this is basically a custom collective on TPUs. If you've used JAX, you've seen psum, allgather, ppermute maybe. And this is basically a ppermute, a very, very simple ppermute implemented with Pallas. And the idea here is that you have, if you're using, let's say, a V5E in a ring arrangement or something like that, you may want to send everything to your left or to your right neighbor. And this is a kernel that does that. And you basically query your current access index, and then you compute your neighboring index. And then you use, basically you have a little bit of a synchronization between you and your neighbor, and that's this like semaphore signal, semaphore wait. And then you use async remote copy, which basically gives you back two futures when you're done sending to your neighbor. And then this is the receive that your neighbor is sending to you. Your left neighbor is sending, if you're doing a right way, like a clockwise, if you will, collective per mute, someone will be sending to you. So this corresponds to you sending to someone. This is corresponding to someone else sending to you. And yeah, the story is the same, where you just take this kernel and call it inside a Pallas call inside of a shard map. Yeah, and that's kind of the main last demo I had. Yeah, any questions about this? This is also something I feel is potentially very powerful, especially if you want to write your own kernels that overlap the communication with compute.
Questions? We're almost at time.
Just quick question. Is this notebook public? Can we return back to that later?
I'll be sure to make an external version of it. But yeah, all the features used in this notebook are public.
All right. Thank you.
Thank you, Shard.
Right. Thanks.
Okay, I believe there's now time for a happy hour. So let us not keep you from this. I think it's actually in a slightly different location to where the rest of the meeting was, but